Hello, partition labels. Read. You're given a string S consisting of lowercase English letters. We want to split the string into as many substrings as possible, while ensuring that each letter appears in at most one substring. Return a list of integers representing the size of these substrings in the order they appear in the string. The string can be split into xy, xxy, zb, zbb, isf. That means so 5, 5, 1, 1, 1. And it should be a substring because xy is a substring of x and xy is a substring of xy. B is a substring of zb is a substring of b. Then I is not included. ABC should split into ABC, ABC, AB, AB. This is correct. Use ABC. Each letter appears in at most. C, C. But we could also do A, it's technically A, AB, ABC, and this. Technically, it's this one. Yeah, this be the substring. I'll watch the solution.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem partition labels. This is a very interesting and somewhat unique problem. We are given a string S, and we want to partition the string into as many parts as possible so that each letter appears in at most one part. And what we want to return is the list of integers representing the size of each of these parts. So let's actually start with the second example this time.
Oh, that's why it's 6. Because they can all be included. And this one, and they all should be separated as only at most once and cannot be partitioned. But technically, yeah, because cannot be repeated. But why not ISL? So it could be 3. Because that's technically ISL is a substring of ISNL. Oh, weird. I don't understand.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem partition labels. This is a very interesting and somewhat unique problem. We are given a string S, and we want to partition the string into as many parts as possible so that each letter appears in at most one part. And what we want to return is the list of integers representing the size of each of these parts. So let's actually start with the second example this time, because I think it really helps to illustrate how to solve this problem and kind of makes it simple. Just starting from left to right, let's take a look at the first character. It's an E character, right? We want to partition this into as many parts as possible, but each character, such as this E, can only appear in a
Once.
single partition. So what we would want to do is just say, okay, cut it right here, right? This is a single partition.
But there's an E
Great,
in the
but
end.
we can't do that. Why can't we do that? Because there's actually multiple E's in this string. There's another E all the way over here, and our partitions have
So
to
if
be
it's not the same,
contiguous. As soon as we see the first character and we see that it actually occurs way to the right in the string, we will never be able to partition the string here, 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 anywhere, right? Because at the very least, we know that this has to be one partition. And if we do partition it like that, this I think is 9 characters. But we actually can't
you have another
even
C.
partition it here either. And we can figure that out just by looking at the second character. The second character is a C. Now there's a C over here, there's another C over here, and that's perfectly fine. But the reason we can't partition here is because there's a C in the last position. Only by looking at the first 2 characters, we realize that the entire string is going to be a single partition. We can't partition this any further. And so what we're going to return is we have a single partition, and the length of that partition is 10. So this is the list that we are going to return in this case. So you might be starting to get an idea of how we can solve this problem in general, but if not, don't worry about it because that's exactly what we're going to talk about right now. So let's take a look at another example. In this case, we're given a string and the result is that we can split it into 3 partitions. The first partition is going to be 9 characters, the next partition is going to be 7 characters, and then the last one is going to be 8. But let's try to figure out how we can arrive at that solution and how we can make it as efficient as possible. So let's take a look at this string and let's use the similar idea that we talked about in the previous example. So we look at the first character, it's an A. Now immediately
So
we
extend
know
it
that
until
we
we
can't
what we thought.
partition this at this point, right? This cannot be a partition if there are additional A characters somewhere in the string. And not only that, we could have multiple A characters, and we do. We have an A character here, 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 and that's the last one. Now, which one of these do we care about the most? We care about the last A character the most, because once we stop here, we know for sure that all of the A characters are in this portion of the string. And that's what we're trying to do. We're trying to create partitions where all A characters are going to be here, not anywhere else in the string, not in any other partitions. So
There's also a
wouldn't it be
possibility of
convenient
second
for us
and a
every
third.
time we see a character, if we could automatically know where the last index of that character happens to be? And maybe, just maybe, this character itself could be the last occurrence of A. This index could be the last position where A exists. Well, conveniently for us, we can do exactly that, and we can create a hash map. So we can create a hash map just like this one, where we take every single unique character in the input string and we map it to the last index that it occurs at. So for example, you can see the indexes are a little bit messy, but we can see that A ends at the last occurrence of A is at index 8. So we could map A to the character A to index 8. The last occurrence of B is going to be at index 5. Now, I could do this for the entire string, but we have a ton of characters, so I don't want to waste my time too much. But just assume that before we even start iterating through the array, we build a hash map just like this one. And the time complexity of building this hash map isn't going to be bad, because all we have to do is just iterate through the entire string. So the time complexity and the time complexity will be O of n. Technically, we're guaranteed that every character in here is just going to be a lowercase ABC character. So the memory complexity of this hash map is really going to be, big O of 26, so constant memory complexity. Not too bad. Okay, now before we start iterating through the array, let's think about how we're going to approach this algorithm. Remember, we are going to have an output, which is going to tell us the size of each partition, as you can see up above. So it would be helpful for us as we're iterating through this if we maintain the size of the current partition ourselves. Initially, we can set that to 0. And as we iterate through this, for example, we get to the first character, we see it's at index 0, but the last occurrence of A is at index 8. So we can keep track of another variable. Let's call it end. You could call it whatever you want, but end, which is going to tell us what's the end of our partition as far as we know so far. Right? Because we see the character A and we know it exists, the last occurrence of it is over here. So we assume, so far we're assuming that this is going to be a partition, but we don't know for sure just yet because we have some B characters here. It's possible that one of the B's exists even farther than that, and if that's the case, then of course we have to update our ending. But in this case, that's not the case because the B's are actually within the first partition. So let's see this algorithm in action. Okay, so far our size is 0, we get to the first character, our end is 0 so far, but we know that A, the last occurrence of it, is at this index, so we update our end to be index 8. We get to the second character, B, the last occurrence of it is 5. 5 is less than 8, so we don't have to update our ending just yet. And by the way, actually we'll have incremented our size, we'll have incremented to 1 after we iterate the B or the A character, and we'll have now updated it to 2 after we have visited the B character. Again, we get to an A character, so we know that we don't have to update our end because the A's last occurrence is still here, but we can increment our size now to 3. We see a B character, we've already seen it before. Okay, now we see a C character. We've already seen a B before, so we can go ahead and update the size to 4. Now we see a C character for the first time. So where's the last occurrence of a C character? It's all the way over here at index 7. Of course, we're going to get that from our hash map in constant time. Since it is a 7, we don't have to update our end again. So we are good to go, but we can increment our size now to 5. Now we get to another B character, so no major updates here. We get to an A character again. We get to a C character again, no major updates. But at this point, our size will actually be 8. Now we get to the last A character. So now our size, this position, we're at the index where our end value happens to be as well. So what that partition, the size, because starting from here, we're going to be looking at. So that means we're going to update our end pointer because 14 is, of course, greater than 8. So end is now going to be 14. Of course, we are going to increment our size now to 2. 4 they're at 12, which is 13, less than 15. So E, this is the last occurrence of E, and it's exactly our end value. So this end 7 is now to be 2. Next character is F. Last occurrence of F is actually at this position, so 11 is less than 4, our end. So that means we're going to update our end pointer because 14 of F is actually at this position, so 11 is less than 15, so no changes here. We see another E. We've already seen E's before. They're at index 15, which is what we have. No big deal. We see a G. And G is, the last occurrence of G is actually at this position as well, which is 13, less than 15, so no updates. At this point, our size will actually be like 5 now, I think. Next, let's get to D. This is the last occurrence of D. We get to E. This is the last occurrence of E, and it's exactly our end value. So this is the our size. So 20, don't really up the size. Remember, the first thing we want to do is do a little bit of pre-processing. By that, I mean building our hash map, where we are going to be going ahead and mapping every character to the last index of it in the input string S. So let's go ahead and iterate through our string. In Python, we can save like one line of code by enumerating the string, which is basically going to allow us to get...
Oh my god, I hate functions. Of course, enumerate the values.
To iterate through the index and the character at the same time. So I is the index, C is the character. we're going to go ahead and take that character and set its last index equal to I. Now, this is okay because even if the last occurrence of that character isn't this index, eventually we will have visited the last occurrence of that character in the string, and then we'll have updated the last index of that character to the last occurrence. So this is pretty simple. Now getting into the actual algorithm, we are going to be doing the same thing. We're going to be enumerating through the index and the character of every single character in the string.
Okay, so for each character, make that make the value inside of the character equal to the index. So that means the map of where that character is updated to I. And will this like update the last index?
But remember, we're going to be maintaining a couple things. One is going to be the result, of course, which is going to tell us the size of each partition. And if we want to, add the size, we have to maintain the size. And we're also going to be maintaining the end of each partition. So initially, these can just be set to 0. Now, as we go through every character, as soon as we see a character, we want to go ahead and increment the size of the partition. We also potentially want to
Wait, I have to enumerate? Why not? Let's do this, bro. I don't need on my index. Well, if I did come up, but index I, well, technically it's gonna be index rather than a value. So it's gonna get the wrong character. But we can also get the character based on X arguments I. Then split the character, get it here. What we can do enumerating instead, like she said, there's values. You don't have to do standard unknown. So
update the end of the partition if the last index of this character is
this is easy now. Get the last index goes to last index up 6 goes I. That means the character now maps to the last index because it's gonna keep enumerating. And apparently it can be updated. Man, I'm getting feeling crazy. But yep, there's my rest. Okay. Now we enumerate again. Or I need to enumerate again in X. Right. That's then size plus equal 1. Then size dot push it once we find that the that I no uh, that the last index that character is now equal to I. But once we find that the last character now maps to the I value, if the character, so if the character is now equal, no, because so if the Well, continue, even if I don't know. C is equals to I. Well, technically, update the map. So the last index at index C, that means that's the character. Is equal to the C S at index I. That's correct. So this one gets this the character at that certain index. But yeah, what if this was 2 and the last index at index? Well, technically they're not equal because the character there in which it's contained in will now be 4. Well, there's there's a gap here. But I'm if that is the case, then the rest of it size out and different is actually enumerates each S. And then we will update the end value. Ah, and the side. Hmm, this is wrong. Let's continue.
Have
Yeah.
last
It's the
index
next
of
of
that
that
character
character.
each partition. So in addition to
Oh my. Of course I have to utilize the end. The character at that value is greater than the end value. Oh my god. Then the character and oh my. So confused. Oh, I
that
didn't.
last index,
I
you can
haven't
write
thought
it
of
out
that.
like an if statement
I haven't thought of that. The last index at index C will always. Ah, so that means I have to
like
now
this,
check
but
first. I should compare first to the end, then update it. That's the end value. Then we can now make the end value equals to the last index. And now, once we do that, once we up, we this keeps updating every time we find a new character and updates it if it's greater than the current end.
to save a line of code, we can actually just use the max function, which is built into
Yeah, that's also good. So n equals max between as index and index C and
Python and most languages. We can update end to be the max of itself and the last index of the current character that we are visiting. So we can get rid of these two and just have this one line of code. Remember,
then after we get the end value now, once we once I is equal to the end value now, I wait is I no if I no is if size is now equal to surely 9, then n would be if size minus 1 is to the n value, because surely the n value is 0, 1, 2, 3, 4, 5, 6, 7, 8, and minus 1 equals 8. But let's continue.
we know we can stop a partition if we actually reach the end of the partition. So if I equals
Why not size?
the end of the partition,
I mean, technically, does this work as well?
then
Then we can now rest on append size. Well, technically, yeah, because I mean, you don't need to do the I though, technically. But then again, size resets and it will, once it resets to the next partition, it will technically never happen and will go out of bounds. Yeah, I is correct rather than size minus one. So append size, then size is equals to zero again.
We're done. We're going to go ahead and add the size to the result, and then we can go ahead and
And this
reset the
should be,
size back down to 0. And that's
and
all we really need to do as we
and
finish
we
our
can now
partition. We don't really have to
regress.
reset the end because it's not really necessary in this case. Once this is done, our result will have been built, so we can go ahead and return it and then run this to make sure that the code works. And as you can see on the left, yes, it works, and it's about as efficient as we can get this problem to be. So I really hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot. Consider checking out my Patreon where you can further support the channel, and hopefully I'll see you pretty soon.
Thank you for the video explanation. Guys, thanks for watching. See you soon. Let's just bug out. Or screw you. Of course, it's karma. Copy it. Bruh. Submit. Yay.